I got asked to give a slightly cutting edge talk, so the slides here have just been compiled about 5 minutes ago. So this is a live bit of functional programming, and to give you a sense of motivation, I wanted to explain why we've been working on this very long-term project. And the project started from a frustration with operating systems in general, because we're building layers and layers of software, dropping it onto the cloud with more and more layers of emulation, and the entire software stack is starting to fall apart. Security holes, very hard to program, very hard to manipulate in an interesting programmatic way. And also this frustration with functional programming, because we build these big functional programs and then we compile them with nice compositional properties, and then we drop them on top of about 20 million lines of operating system code, all of which is completely unsafe and is generally a little bit hard to reason about. So when it comes down to it, why don't we just get rid of that code and just try to go all the way down the middle and apply the nice compositional properties of functional programming to everything? So this is what Mirage OS is. The talk is not about this, but I wanted to give you a sense of why we're doing some of this work in functional distributed programming. So it's a library operating system that constructs unikernels that are very specialized virtual machines that are a single address space operating system that run directly on the bare metal. So what is a library operating system? Who knows what a libOS is here? Okay, yeah, about half the room. So libOS, very simple. The idea is that instead of having an operating system surrounding your stack, you link everything that the operating system does as a library, and you provide a very small boot layer. So the problem with library operating systems is that they have no isolation inside the operating system, but with a hypervisor, we get the isolation. And so now we can just link everything from TCP/IP stacks and device drivers directly into the OS. So the point of unikernels, though, is that we have many operating systems. These operating systems, library operating systems, are as old as SOSP itself, the big conference. What we want to do is we want to take high-level languages, so functional programming languages, and link them into the library OS as well. So at no point when coding in our applications should we ever see any kernel code or any low-level code. We have high-level languages like Haskell or Camel or Lang, all being compiled down into operating systems. And in addition to the language code, the application logic, configuration, everything is compiled in as much as it can. So it just gives you a sense of where we are. So the idea is that you take this huge dynamic stack that we normally work with, and then you take unikernel compilers, and then you crunch it all down using as much static knowledge as possible into a single node, single specialized runtime. So we have a bit of a plot your own adventure here. So I can show a demo of Mirage, if anyone's interested, and it would take about 2 minutes, or I can forge on to the next bit. So who has not seen Mirage is interested? Okay, wow, that's amazing. Okay, this is good. So what we have is, so here I have a Zen host, and I want to write a simple bit of code. And now, this one's written on a camel. Who knows a camel? Let's just keep, fantastic, but half the room again. But we've sort of a split between net and PL, I suspect, in this room. So, good workshop. So what we have here, if we can see the, let me just turn off syntax highlighting, might be a little bit easier. Yeah, there we go. So it's an extremely simple hello world program that just says print hello world 4 times. The main difference is that the program logic is parameterized by the outside world. We're saying that given a console of some kind, please run this logic for me. So it's a small fragment of logic. So this could run in multiple ways. I could say Mirage configure ---- Unix, and it compiles me a normal Unix application that prints hello world. Right? Really uninteresting, because all it does is, when I compile it, just builds a normal Unix application. So in this case, mir console prints hello world, very predictable. But because we've abstracted the OS dependencies in the unikernel, I can do Mirage configure ---- and the Mirage tool assembles all of the scaffolding required to just make the library part of it just work. So what's happened here is that when I type in make, I've not done any kernel code, but it's actually linked a kernel. And this kernel here is about 3 megabytes. You can get them down to hundreds of kilobytes with a bit more compiler optimization. This is a debug build. And I can just say construct the unikernel, and it will just run it. So this is obviously a very simple one, but these unikernels are type safe all the way down to the shared memory interfaces. All device drivers are type safe. And they boot in about 10 milliseconds, and generally are very small and easy to manage. It obviously gets a bit more interesting, because on top of this, we can build really quite complex applications. So web servers, SSL infrastructure, and so on and so forth. And it all works because we define configurations that are run on the host that define programmatically the set of device drivers and so on that you might need for all configurations. So for Unix, for Xen, for socket-based interfaces, for TCP/IP stacks run directly, and so on and so forth. So I won't go into details of this, but this is the web server. And you can see just, for example, I can say that give me a network stack when I'm building it that is either the socket network stack we're all familiar with, I can't see my own cursor, or it's the direct OCaml TCP/IP network stack with DHCP or with IPv4. So you can bake in all kinds of configurations very, very deep into the system. So I can show you, for example, a static web server. I can just say, oh, hello NetPL, and we just want to serve that as a unikernel. So then I can say DHCP equals 1, Mirage configure minus Xen, and this will just go off and build for me a unikernel that, again, is a fully type-safe web server that will just serve requests. And let's do make. And we just have to give this one a network interface in this case. So let's give this one, and it doesn't need 256 megs of RAM. Let's give it 32 megabytes of RAM. These are tiny. And then I can just say, construct me the unikernel, and it goes off, it gets its DHCP address, and I can do curl, what was it, 79, and oops, 80 probably? Yep, there we go, we can serve it. So this is just a really nice way of building the small bits of infrastructure that are fully type safe all the way down to the bare metal. So there is a problem though. Unfortunately, every time you solve a problem in systems is whack-a-mole, new problems come up. And this is that we now have the capability to run tens of thousands of these unikernels on a single host because they're so efficient and so specialized to the application. So we've gone from an operating system into a distributed systems problem. So once you have these dust clouds of billions, literally there's billions of Xen virtual machines right now, there could be trillions of these things running all over the place. They also run on ARM as well, so they're fairly distributed. So how do you keep track of all this stuff, right? What on earth do we do? And so we started thinking about what the distributed system of unikernels would look like. And at this point, I justify my existence at NetPL because we've taken the ability to write functional bits of code, compile them into operating system kernels that can boot up an EC2 or Rackspace or any other provider. But also, we have to think about how we map these functions across a distributed system that has the needs of a normal distributed system we might build in an existing OS. And when you look at this, we're coming at this from a clean slate, right? We have no existing libraries, no file systems. We just have a bunch of libraries that we've built, and we can do whatever we want. So it's quite liberating as a researcher, but it's also quite dangerous because you can do whatever you want. So we need to anchor this somehow. And if you look at all distributed systems today, they actually have 3 features that you cannot live without. You need the ability to have persistence for fault tolerance. You need to be able to schedule communication. So anything that magically introduces scheduling tends to not scale because it's a very application-specific problem. And you also have the often ignored tracing. So whenever you have these billions of systems, you want to figure out what on earth happened about 5 minutes ago in that corner of the data center whenever things blew up. And there's many solutions across the existing stack that solves a part of these, but they typically can't solve all of them because they don't control all parts of the software. In a libOS, we control everything. So the question was, what if we just use Git? And this came up in a conversation in the pub because we'd just been using Git all the time for version control. And these unikernels are about 1 megabyte in size. So we thought, why don't we just start checking them into GitHub as well and keep track of those? So now whenever you did Mirage configure, for the last 4 years, the entire set of outputs have also been tracked in GitHub. Slightly against the terms of service, but it works because the Git repository is about 100 to 200 megabytes now. But when you look at the properties that Git provides, it moves far beyond just version control, right? So it provides you with persistence through git clone and git commits. It gives you scheduling by you controlling exactly for every node how you git pull and push, and you can choose which nodes you pull and push to. And it also gives you this obviously very, very natural mechanism of doing tracing and debugging. You can get log to see all operations that have happened. I can get checkout to time travel to any particular node. And crucially, the most incredible feature of Git that is the most rarely used is git bisect, because it allows me to write a function and says go back in time and keep testing this function until you find out a counter point when it doesn't work anymore. So in our live infrastructure in unikernels, we just git bisect to identify a bug, and we just go back in time, leave it, come back after lunch, and it's hopefully found the first commit at which this error happened. So who's familiar with the internals of Git? Who's used Git, first of all? All right. Pretty much everyone's used Git, except for 1 or 2. Who thinks they're familiar with Git? Okay, a few more. So my hand is down because Git itself is actually a very multi-layered system. It's the genius in Git that Linus Torvalds did was he built a very low-level key value store, and this is just an immutable data store where it hashes the contents. Then on top of that, he built a series of structured abstractions. These are all available via the command line, and at various points in your Git careers, you will find that you accidentally destroy some source code, and you have to drop into the low levels in order to repair that damage. It happens to everyone, typically before a deadline. So with Git, you can build up these structured abstractions, and even all of the notions of file systems and merge functions are all actually accessible and hackable, which is why it's just a really nice system to build something on top of. The problem with using Git for data center usage is that it does introduce some problems. It doesn't just work. And the most obvious is garbage collection. So we've now established a fully persistent data store, and it records all operations permanently, so our database will just keep growing. So we need to figure out exactly how we can control this massive changelog and figure out exactly where to store it. A fundamental thesis in this work is that storage is essentially free right now, but storage management is not free. So we can always find a few terabytes or petabytes of disk to dump this history onto, but having to manually manage that yourself and deal with all the resource scheduling is something the system should do. But the fact that you have the storage, you need to put it somewhere, not a problem. Because you never know when this will become incredibly valuable for debugging and offline analysis. And we also already have the tool we require. So Git rebase is an existing bit of Git functionality that replays history and compacts it and gives you a new version of history with a lot of the change sets removed. So we already have the atoms we need. We just need some cunning algorithms. And also, shell control is really hard because if you try to wrap the Git command line, you just don't have very much control over Git. So we rebuilt the whole of the Git protocol from the ground up to deal with this. But fundamentally, we don't have a programming model for Git. Git is something we use to track our programs, but not something we program with at the moment. So it's designed, and a lot of its functionality is designed for distributed source code, but not for the complexities of distributed binary management, and certainly not for operating system management. So the merge functions aren't quite right, and you've all seen merge conflicts before. So in the rest of this talk, it's a slightly experimental sprint, just trying to figure out how can we use this for building distributed data structures we can actually use in a data center as well.
Did you just build like Lamport clocks with the message system and like
right.
instead of I mean, like, so Git is useful to understand what's going on, but like,
right.
Is there any reason to call it Git when you're done with this? Because isn't this just like, Lamport
yep.
timestamped messages?
Well, it's in the same way as, the sum is greater than the whole, because crucially you can use the entire Git ecosystem of tools to interact with the system. So you're programming with Git, but then at any point you can exit from your data structure model, and you can actually use normal command line tools to debug and so it's a bit like vector clocks, but themselves are used, right? It's the systems built on top of vector clocks that are relevant. So I'll actually show that in a demo as well. So it's extraordinarily cool to be able to use Git to fix your actual deployed infrastructure and see all the recompilations and so on trigger off. But fundamentally, though, in fact, let me just talk about that. Yeah, go ahead. Josh.
What sort of consistency model is Git forcing you towards?
So Git has the lowest level consistency model possible in consistency models, which is branch consistency. So whenever you use Git, in fact, here. So let me start off with this one first and answer that question. So we rebuilt Git as a library because obviously we're working in library operating systems. So like SQLite, we rebuilt this database called Ermin. And the intention is that it's the least opinionated library of all time. It simply says, it gives you a library to express how to persist synchronized distributed data structures, both on disk and in memory. On disk, it uses the Git format. In memory, it uses a very efficient IPC format. And it enables a style of programming where you don't have any consistency except for individual nodes can fork a global data store. They can fetch changes from other nodes, and they have to choose which node. And they can merge those changes into their own version of the world, and they can push data back. So this is the consistency model, where imagine everyone here has a completely independent copy of the database, and no one can hear me except for you, and you have to somehow decide how to propagate my words by merging them into your data structure into the outside world. So a near useless form of consistency. Crucially, on top of this, you can then build all the other consistency models that every NoSQL database has built. Everything from React based on the Dynamo papers all the way up to causal consistency and so on and so forth. And it's awesome because it shows you for every form of consistency the set of messages and commits that go back and forth. So the challenge is not how to build a consistency model, it's how to make them fast. But in many, many use cases, you don't want fast. You just want it to work, and you want to see exactly what happened, particularly for configuration management and so on. So the basic idea here is that every node gets a local partial copy of the database. Imagine we just hook into this set of DAGs, and we always be very explicit about how things happen. No magic in the data structures, except when you choose. So this is the basic architecture. I won't go into the depths of Git too much. I do have a tutorial if anyone's interested afterwards, but the basic idea is that every single object in Git is an immutable blob, and you can use a Git hash object and Git cat file in Git in order to access those. And that's simply a hash that's named based on its content, so it can never change. On top of this, Git builds an abstraction of a DAG, and this is kind of the vector clocks, except just a bit more connected, where you can build trees of commits and file systems that all map onto these blobs. And then you build a slightly human-readable tag store that tells you the branch you're working in. And so this is the only mutable part of the system. Anytime you change a file, you fork and copy this entire set of pointers, and then you point the head branch or the P2 branch at the next thing. So space, definitely a problem, unless you have lots of space, in which case it's not a problem. If you run out of space, you're dead in the water. So the essence of the system, though, the challenge around programming is, what do these data structures look like? And these data structures are pretty fun, right? So this is a little bit of a camel code. So for those of you who don't know a camel, we can just define arbitrary data types in a camel, like type T could be apple or orange or pear, could be an integer, whatever you want. And then the crucial thing is that because we're working in Git, anytime we diverge and we want to reconcile, we define a merge function. And the merge function operates on the two copies you're merging, but it also understands the ancestor from which it sprang. So this means that unlike vector clocks, you're not trying to do two-way merges where you don't have a lot of context about where something came from. You always know a common ancestor or multiple common ancestors where the system originally diverted from. So these merge functions can figure out the set of differences in both sides and define data structure specific mechanisms to reconcile. So in a network where you have lots and lots of nodes, you might have some data structures that are disconnected for weeks or months on end, and eventually can always follow back their provenance to figure out what's happening. So this is amazing for very, very large scale, very, very lazily reconciled systems. And at any point, every data structure only has to define how to do a merge or define a conflict. So the worst case is you try to do a merge and you have no way of figuring out what's going on, and then you reconcile. But in this case, we're trying to define data structures that always have a well-defined model for doing that. And so if we can come up with data structures that always never have a conflict, then you have conflict-free data structures that compose at the cost of requiring the storage space to pull this off. How am I doing for time? Oh, half an hour. Oh, I thought it was a 20-minute talk. I'll slow down. We have
20 minutes.
Oh, we have 20. Oh, plenty of time for demo. Perfect. All right. So let me give you the simplest example for how something should work in this world. And it's logging. Logging is something that always looks quite simple until you try to build it. And conceptually, if we want to define, even before I move into a demo, what is a log? Imagine we have petabytes of logs with thousands of nodes or hundreds of thousands of nodes. It's basically a list of a string, which is the log entry, and a timestamp. And this timestamp is monotonically increasing as time marches forwards. So if we just say, how do we define a mergeable log system? Well, it's pretty straightforward. Timestamps must always be increasing. So if we're merging from two systems, you always insert the timestamps such that they're monotonic. You maintain the invariant. And if we have equal timestamps, we say that they can be in any order. So that's fine. And with this logic, we can now have conflict-free data structures for logs, because there's no situation in which I can give you a set of logs that don't merge. And then every node in this world, we want to also keep track of when a node locally built its logs, committed locally, and then push all of that provenance to the outside world. But at the end of the day, end up with a single log that is monotonically increasing. And this is what we can do. So let me show you how Ermin works. If my compilation finished compiling, so we'll just launch the Ermin daemon. So at this point, yay, we have. I will come back to that. Don't worry. So what I'm going to do is I'm going to I've actually written here. Let me just show you the program. What I've written here is a simple OCaml program that I will turn off syntax highlighting again. It defines how to define the data structure and how to do the merge. So we'll obviously skip past a lot of the boilerplate code here, but the critical bit here is this is the bit of the data structure that says that this is the type of any entry is a timestamp in the string. and then we can move on to define how to convert to JSON and so on and so forth. And then fundamentally, we are saying that the type of our log file is taking one of those entries and making a list of those. And so the key to our log file is a path, a string list, and then we have a list of entries that define the log file. So then later on, we can programmatically go and define, I'll just skip forward a little bit, I'll find the merge function. And so the merge function here for the log files is pretty much what I described earlier on. It's a very small, with a little bit of boilerplate that simply says, merge the two sides in monotonically increasing order, and then just return the result. So pretty straightforward. And what the example does is that afterwards, it then goes off and actually creates a toy demo just for the purposes of this, when we can branch the store, we can add some log entries to it, and then we can reconcile them. So I will just show you this working. Obviously, in a realistic system, there's more examples afterwards. So I will start custom merge, and I will go to my little web interface. And what is happening here is that this web interface is telling us the state of the database. So we're now connecting to one node of the system, then a test node added on, and then they're both independently adding their log entries into it. And eventually, they'll both decide to reconcile. And so the test and the master will merge. So what's happened here is that the test node has independently been acting. The master node has been doing its thing. Then it's decided to go check it and test, and it's pulled in all of its history into itself. So if I now look at the actual operation from a different perspective, so I will start doing this, except I will use the git command line tool in order to debug it. So this kind of answers the question about why this isn't just a direct log. So this is a normal git log where we're using the git command line tool to look at the database, and we can observe the branching and the mechanical properties of the system just by using the command line. So this means that so I'll just show you the shell script there. This literally is saying, oops, 2 layers of shell scripts. I'm sorry. And this is just saying that while true, do git log with a very fancy command line to give you the format that we saw. But it gets more interesting as well, because the mapping into Git, so this is, can everyone see this at the bottom? I'll just make this a little bit bigger. So if I do git log in my directory, we can see all of the operations at the low level. And I can say git checkout, a copy of it. And here I can say, here are the log entries. And these are log entries the machine's added. But then I can just say, oh, I'm coming in from the outside world, and I would like to actually make a difference. I would actually like to commit a change into the database. So again, let's say hello NetPL, and this is me as a human, so I will just sleep 3, and git commit -a, Anil was here, and this -n. So at this point, if I shift back to my database, what's actually happened is that once that commit goes through, it bidirectionally maps back into the data structure. So you have a lens. So Git has actually turned into something where I can program it and run it against the system, but then at any point, the system can go back and give me a set of changes back that I can reconcile and map back into my data structures. So this means that Git has now turned from just a dumb logging point into this distributed branching heap, where anyone can go and drop stuff in, and we define the semantics in our data structures to map things back and forth from there as well. So imagine you have a data center with lots and lots of operations going on. You have Sriram's flow rules, all logging with all the differences and so on. And Ermin provides this invisible backend where you can record all these things and actually keep track of all the changes going back and forth using the existing tools.
What happens if you enter invalid content?
Yeah, so you define that in the data structures. So whenever you pull change sets in, you have to say, well, I have a pickler and an unpickler. And then if the unpickler doesn't work, often they just usually discard the changes. Quite often, though, most of the data structures have some other thing. So you can just say, I didn't know what this was, but I'll propagate it through as an opaque abstract node. And then you can run linters and stuff over them in order to just check that you don't have badly behaved programs in there. One of the key challenges here is we're adding multi-language support at the moment. So the multi-language support is fascinating because I want to commit in some camel code and have some Go code read it on the other side. How do you make sure that these merge functions agree? And so we're trying to figure out exactly how to build a data structure such that no matter what the other side does, there is some sensible semantic at the same time. So this is definitely ongoing work at the moment. So it only gets really interesting if you have usable data structures, because with usable data structures, we can actually start programming at a slightly higher level. So let me give you an example of two very simple data structures. First one is queues. Every data center needs a good queue. In this case, queues unfortunately have as many definitions as there are queues. Because what if we have a distributed queue? So this half the room, this half the room, we're both adding work on, we're both popping work off. What order do we do things in? Well, in fact, the only answer is what our goal is. We just want to define a semantic. We don't want to impose a semantic on this queue. So what we're going to say is that there's a sequence of operations that this queue must satisfy. And in OCaml, this is a signature. This is just like an interface, except slightly simpler. We would say that, well, we have the ability to create a queue. We can get the length of the queue. The queue is abstract in terms of the type of elements it holds. We don't care. We just know that whatever element it has, we can push onto it and get a new queue. We can pop an element of the queue and get the element and a new queue, and we can peek as well. And crucially, unlike a normal queue in OCaml, we can also merge. And the merge is the operation we define that gives it its distribution properties. So this is actually a functional queue built in Ermin. Looks kind of scary, but it's actually simple. So every queue in a functional queue normally has a push list and a pop list. And this is just a way of keeping track of the operations in a purely functional queue. In this case, we define two queues here, I0 and I1. And a queue consists of a pointer to the top of a linked list and the end. And then this one consists of a smaller one. So if you look at I1, it consists of these nodes, N11, L12, N13, N14. So this is a 4-node queue. And you notice that the elements in the queue map into the low-level Git store. So N11 and N12 were actually the same object, so they just map onto the same object. Then I0 consists of its own larger queue, and then it includes the smaller queue, but the actual contents, again, are all stored and deduplicated. So we can do all kinds of operations, and it'll do its very, very best to make sure that this the low-level kind of storage of the elements is as small as possible. But then meanwhile, it keeps track of all the pointers required to handle the queue. Now, so let's take this queue, and we want to define the semantics for the queue, which is that whenever we pop some work off the queue, it's okay to do that twice, right? Idempotency is defined in the queue, because it just means the work is repeated. But if we push stuff onto the queue, we want to define an ordering, and that is an error if we're trying to merge. So this is our definition in the data center. And so we implement this, and this is the original data structure. On the left, it forks off, and it adds E. And then it forks off, and it pops A. And then it goes off and tries to merge. Meanwhile, in I2 land, it's popped A, and it's pushed on two elements. And then it goes off and tries to merge. So what happens here is that the Ermin system can inductively just go through the data structures and figure out, well, saying that, well, in this case, the A popping operations were repeated, so it's okay, and then both of those are conflict-free. But then it requests the application to say that given that you've added on two different nodes, in this case you've added on E and F and G, how should those reconcile? And the application tells it, well, E comes before F and G. In this case, it's lexicographic ordering. And so you can see that the end result represents exactly that provenance. There's no unnecessary nodes there, and there's lots and lots of nodes added on here as well. So the purely functional queue, without looking at the OCaml code, simply defines the semantics for this as well. And the good thing about this is that the complexity of these data structures is actually very, very reasonable. So normally with a queue, you push, pop, and merge, and we understand the complexities. In the case of Ermin, the merge operation is currently linear on the number of nodes, but with a bit more cunningness, we're making that log n. So it's simply an algorithms problem at this point, trying to figure out how to traverse the graphs and so on and so forth. So a second one, a very quick one, is mergeable ropes. So in the case of logging, we have petabytes of data in a data center, and we want to figure out how do we immutably handle a lot of these strings that come out of it. So a rope is a data structure that immutably lets you manipulate large strings, for example, or any other element, but strings are a very common one. And you can insert and delete and append and push directly into the strings themselves. And also define a merge operator. Now, the problem with these is that the contents can be massive, right? You'd never want to touch the contents if you can avoid it. So in this case, we can actually define some merge operations that are quite interesting. So here we define lorem ipsum and doemet. And on the left-hand side of the fork, we've actually added a node. And we've also, on the right-hand side, added a node in a different place. Now, the important thing is that we don't want to have to traverse the entire system like we did last time in order to figure out if these can merge or not. So what we do is, in this data structure, is we say that the naming of the nodes is a hash of what came above it. So we've created a hash of hashes, almost a Merkle tree. And in this situation, what happens is that we can simply walk down and look at the left and the right-hand side branches, and we can keep walking down, and we can say that, well, these are all still the same, except at this point, when we walk down here, we notice that this node here is different from this node here. It's got a different name, and we can build those up. And then we can start doing the merges, so we just keep building them up. And then by the time we get back here, at 10, we finished our merges, and we've built up our data structure. So in this case, the merge function simply has to walk down and just check, is this the same on this side and this side? In this case, it is. And on this side, it's different, so it then builds it up from scratch. So these merge functions are arbitrarily powerful. They just walk the graphs, and you can do two very, very different strategies in order to figure out how they merge. And of course, as people are building more and more of these data structures, there's tons of examples about how they all work. So I won't talk too much about benchmarking, but the basic thing here is that we want to use this inside operating systems. So making this stuff fast is really, really important. And the thing that surprises us is that you can benchmark the system itself, and there's lots of numbers here where the basic thing to take away from this is that this is the on-disk version, where it does the Git strategy of committing. This is the in-memory version, where it's using very, very efficient IPC and lots of tricks in order to build the graph without writing it. And this is good enough. What surprised us was when we actually applied this to real systems like Zen, was that it sped up the entire system because the semantics of this were conflict-free. And so normally when you build any kind of operating system code, somewhere in there you shove in some slightly ill-defined notion of transactions. And that requires locking and backoffs and so on and so forth. In the case of Zen, this exists in the core database that Zen runs. And by porting it to Ermin, there's a NSAI paper on this here, we simply eliminated the need for backoffs by defining all the way through the system and thinking through what it meant to be a virtual machine booting in parallel with another virtual machine. And we defined merge functions that were defined to be conflict-free. So this, even though the straight line is a little bit slower by a constant factor that's not too bad, you get the ability to debug and do all of the good things in a very, very natural way. So where we are is that we've actually been building up lots and lots of things using Ermin. It's been a very low level effort to build this graph store. And then obviously as you go up through the layers, we're building up more and more tools. And I thought you might like to see just some of those tools. I'm not going to show you a demo of Dog, but the idea is that if you actually want a really slick logging system, you have to do some work. And what Dog does is that it lets you just give you a command line tool, no libraries involved, where you can listen for logs, and you can have a client that pushes logs. And the really cool thing is that you can actually back this on GitHub. So we can say that if we don't have any actual infrastructure, but we have all these cloud providers, well, I'd like to just define Unikernels that run on Amazon EC2 and use GitHub as their storage mechanism. Well, in this case, because we're using Git as our backend store, you just push and hope that they don't notice if you're storing too much data on there. But for things like logs and so on, things that you might otherwise store on there anyway, or you have your own Git infrastructure, this is actually a pretty good front end tool. One other interesting one is actually JavaScript. So there's actually the other elephant in the room with any network programming, which is that the endpoints are almost always browsers. So we said, well, this Ermin thing is super low level, right? It compiles into an operating system. So we then took the entire system and compiled it into JavaScript, into about 500 kilobytes, actually using the JSFCaml tool that Facebook use and a bunch of other people use as well. And this one's interesting because it shows just how portable this new generation of Unikernels are. So, yep, fine, it's perfect. It's only a 2-minute demo. This is great. So what we have here is a unikernel that is a to-do manager that we now use for tracking our unikernel to-dos. And it runs purely in the browser, and it maps all of its storage abstractions into the browser. So everything I described about Git is compiled into JavaScript. So it means that when you build a web application like this, we can use the backend store of data structures running inside the browser, inside the data center. But we can actually show in these tabs the history of everything that's happening. So I can say, for example, look at this page, and give it a context. Oh, I don't have any context. I haven't initialized my store yet. Let me just edit this log entry. Hello, NetPL again. I'm saying hello to you guys a lot. Here, and then what happens is that it commits it into its local store, and then on this side, it live updates on the other tab by telling you that this thing has changed. And the live update happens through something called, in JavaScript, you actually have a SQL database in the browser. We obviously don't need to go into too much detail about that, but it's something called IndexedDB. And all of the Git stuff just maps into data structures running in the browser. So we now have the ability to commit Git on Unix, on Zen unikernels, and in the browser as well. So if we stop this though, the reason this is interesting is because when you build these high-level applications, we define the merge functions. So let's say here, for example, I introduce a deliberate merge conflict. Hello, my name is Anil, and in this case, I am from Cambridge. So notice I have not committed either of these, but I will commit the I am from Cambridge one, and then I'll shift tabs, and then I will commit the my name is Anil. So what's happened here is that exactly the same data structure definitions that we had before have rippled out merge conflicts. In this case, this is kind of a rope-like data structure with a tree. And the application has seen that there's a merge conflict, and it defines a reconciliation function. In this case, it just keeps both the descriptions. And so the ability to do this, to just say that I want to reuse a bunch of libraries for the basic low-level plumbing, and then just write a merge function, which is the essence of my particular application logic, is how we think this will scale to data centers and browsers and everything. Because it just means that you have all the benefits of the logging and the tracing and so on. You can map this onto almost any operating system possible, and then I can just say, well, I'm building a to-do app. Nothing will ever solve all the merge problems for all apps, and I just define a function that says this is how I plan to resolve it. So this is just to give you a sense of how portable the whole notion of Git programming is. And I do think it's important to also tackle the browser as well. A lot of these programming solutions will only ever hit the data center and so on. In this case, it'll hit them all. So the final one is probably the biggest port we've done, which is we've taken the entire Zen tool stack. And the Zen tool stack is obviously fairly mission critical on EC2 and Rackspace and so on. And every virtual machine boot requires about 80 to 90 RPCs. And tracing this has been a nightmare. So in the last 12 years of Zen, there's obviously probably about 10 billion virtual machines booted. And if something goes wrong in one of them, we get blamed. So how do we figure out what happened? And so this is totally worth this entire effort just to fix this problem, because it's quite annoying. And what Dave Scott did from Citrix was take Ermin, and he ported it such that whenever you do a virtual machine boot, this is the graph I showed you, except this is the entire hypervisor domain, and you can see all these deep merges happening, all being debugged via Git. And this is what I meant when I said that we sped up Zen, because now Zen, the tool stack, is not only incredibly fast to coordinate all these things, it's also got the ability to debug them just by doing a git clone and seeing exactly which virtual machine was trying to merge which transactions, and to go through the entire set of operations. So this has basically convinced us the whole thing is quite usable, and it definitely works. So where we are is, to summarize, and this is just obviously OCaml's good, but it basically let us prototype complicated data structures very, very fast, and it compiles to all of these backends that we care about. But fundamentally, we've convinced ourselves that Ermin is not entirely insane. There's still a lot of challenges left. So for example, we need to figure out the garbage collection in a very structured way. Right now, everything is logging, stopping the world. So we need the equivalent of distributed garbage collection except for Git. But we know how to solve that now. But it's starting to expose HTTP REST APIs. The bidirectional operation has been incredibly popular. So people can go in and manually fix problems in the database and see it reflected in a running system. But the essence of it is this notion that our data centers are turning into tiny fragments of code operating over these purely functional data stores that we now understand how to surface in terms of tooling and usability. It just turns out we had the tooling right under our noses for a long time, and we sort of ignored it. And this is an effort to fix it, and then just bridge the gap between how we handle our source code and how we handle our actual data centers. So I've got tons of active trees on here. I had a few conversations with people around here, but there's lots and lots of ways that you can map existing systems onto this. We're modifying operating systems to git commit all of their changes. We're building up semantics for POSIX. We have a SoftBake paper on that if anyone's interested in understanding how this fits together, and generally making it usable throughout the year. And I'd love to hear any criticism or feedback or crazy stunts that we can do with that as well. So that pretty much wraps up my whirlwind summary, and happy to take questions. Did I ever answer your vector clock question?
Which one?
The vector clock one?
Yeah, more or less.
Yeah.
Which is yes, but you get slightly better semantics. It's not just vector clocks. It's actually a DAG, which is
right.
Slightly better than slightly better than vector clocks, and then you get git tooling on top of it.
Yeah, in many ways you can view this as if the three-way merge is a combination of vector clocks that give you the common ancestor. This is why it's different from CRDTs and a lot of the systems that use two-way merges. So a lot of things are simpler.
CRDTs just invent a lattice, which gives you your parent, right? that's sort
Yeah.
of the...
Yeah, but they're very limited in what they can do. So here you can just build existing.
Because inferred, not explicit.
Yeah. The important thing about this is that you can take existing data structures in many cases and make them slow but mergeable, just by assuming strong consistency of heaps, and then slowly chisel away at them to make them more distributed behind the same interface. So it works out pretty well.
Maybe the bravest presentation I've ever seen. How many live demos you did?
I will admit that 2 out of the 4 demos failed 5 minutes before, so that's why I skipped them. But it mostly worked.
All right.
Lovely. Thanks, everyone. I think it's
Thank
done.